You know, the device you're watching this on right now, it only exists because of the microchip. It was invented way back in the late 1950s by two different people at pretty much the exact same time, Jack Kilby and Robert Noyce. They worked completely independently, they even shared the Nobel Prize for it. But, and this is the key, their inventions were fundamentally different. So that's the real mystery here, isn't it? If they both invented the microchip, how come one design became the blueprint for, well, everything electronic we use today, while the other basically became a museum piece? The answer, well, it's this incredible story about the difference between a great idea and an idea that can actually change the world. So take a look at this. This really shows you the two approaches side by side. Over on the left, that's Jack Kilby's brilliant proof of concept, and on the right, you have Robert Noyce's elegant manufacturing solution. This really gets to the core of our story. It boils down to this. Kilby showed it could be done. Noyce showed how to actually do it. For everyone. Okay, so the first huge difference, and this is a big one, comes down to the very foundation of the chip itself, the material they chose to build it on. This base layer is called the substrate. So Kilby, who was over at Texas Instruments, he went with germanium. And look, that made total sense back then. It was the standard, the go-to material for transistors. But Noyce, up at Fairchild Semiconductor, he made a totally different bet. He picked silicon. And you might think, okay, big deal, but trust me, this one choice, it changed everything. So why? Why did silicon win? Well, this table really breaks it down. For one, silicon is just way more stable when things get hot and electronics get hot. But here's the absolute killer feature. With silicon, you can grow this perfect, super thin layer of glass, that's silicon dioxide, right on top of it. It's like it was made for it. This layer is a fantastic insulator, which, as you're about to see, was the key that unlocked the whole thing for Noyce. Germanium? You just couldn't do that reliably.
All right, so you've got all your little components, your transistors, your resistors, all on one piece of stuff. Awesome. Now, how in the world do you wire them all up? This was the next giant hurdle.
And you can see it right away, Kilby's approach. I mean, it worked, but wow, was it messy. He literally used these tiny gold wires that some poor technician had to solder by hand one by one. They called them flying wires. Then you look at Noyce's chip, and it's like something from a sci-fi movie. No flying wires at all. The connections are somehow part of the chip itself. And that right there gets to the heart of it, scalability. See, Kilby proved you could cram all the parts onto one block, but hooking them up was like building a ship in a bottle. It was a craft, an art form. It wasn't something you could mass produce. Noyce's method, though, using these deposited aluminum lines, it was designed from day one to be made by machines, over and over and over again. So, what was the secret sauce? It was this thing called the planar process. And we gotta give credit where it's due. This was actually invented by Noyce's colleague at Fairchild, a guy named Gene Horney. Remember that perfect glass layer on silicone? Well, they could basically etch tiny little holes in that glass wherever they needed a connection. And then, get this, they'd just evaporate a super thin layer of metal over the entire surface. The metal would seep into the holes, make the connection, and the rest would just sit harmlessly on top of the glass, forming these perfectly flat printed wires. Just brilliant. Okay, so all of this, the silicon, the planar process, it all leads to the final knockout blow, actually being able to make the things. And honestly, this is where the two designs stop being just different and start being from like completely different planets. I mean, just look at the difference here. It is absolutely night and day. On one side, you've got the reality of Kilby's design, a person hunched over with a soldering iron, a rat's nest of wires. It's slow, it's expensive, and one wrong move and the whole thing is junk. You could never build a billion of those. And on the other side, you've got the clean, elegant world that Noyce's design made possible. This is the birth of modern automated manufacturing. The magic that makes all this possible is a process called photolithography. Think of it almost like screen printing a t-shirt, but on a microscopic scale. You're basically using light to print a photograph of the entire circuit design onto the silicon wafer. This lets you create millions, even billions of connections on hundreds of chips all at the same time. Try doing that with a soldering iron. No way.
Okay, so let's wrap this up. When we look back at this tale of two inventors, what's the final verdict?
It really just boils down to this simple idea. Kilby gave us the mind-blowing proof of concept. He answered that first huge question, is this even possible? But it was Noyce who gave us the scalable reality. He answered the next, just as important question. Okay, cool. Now how do we make 1 billion of them? And we can't overstate Jack Kilby's contribution. His was that monumental what-if moment. The idea that, hey, maybe all these separate parts of a circuit can live together on one single chip. He laid the entire conceptual groundwork. And then you have Robert Noyce's genius, which was different. He looked at that concept and immediately asked the engineer's question, the businessman's question, how do we make this real? How do we make it work in the real world? His solution, that combo of silicon and the planar process, it didn't just create an invention, it created an entire industry. So what's the big lesson here? What should we take away from all this? It's that a truly world-changing invention is almost never just a single flash of brilliance. Yeah, you need the amazing idea, of course, but you also need the elegant, practical, and scalable process to bring that idea out of the lab and into the hands of millions or even billions of people. One without the other, it's just an interesting prototype. And, this principle is absolutely timeless. It really makes you stop and wonder, doesn't it? What incredible, brilliant ideas are out there right now, sitting in a lab somewhere, just waiting for their own Robert Noyce to figure out the manufacturing solution that will, once again, change everything.